We propose a novel semantic LiDAR scan completion approach based on the diffusion model, named DiffSSC. 3D LiDAR cannot measure the occluded regions and gaps between sweeps. To provide dense and semantic scene representations for downstream systems, semantic scene completion has been proposed to estimate the missing semantic point cloud. We complete semantic scenes using a diffusion model as the core component, supported by semantic segmentation and refinement modules. The raw LiDAR point cloud is semantically segmented to generate initial semantic logits. The semantic point cloud is upsampled and undergoes a forward diffusion process until Gaussian noise. Then in the reverse denoising process, a denoiser takes the original semantic point cloud as a conditional input, then predicts and removes the noise to recover the dense semantic scene. To further enhance the generated scene, we use a refinement model that increases the density of the point cloud. The architecture of our denoiser is based on MinQNet, while inserting the information fusion module between layers. Given the feature extracted from a layer of MinQNet, we integrate the conditional input and step information between layers to obtain the fused feature. We train the denoiser using augmented ground truth by generating training pairs through multi-step noise injection on the ground truth. The denoiser attempts to predict the residuals from the noisy ground truth, while we encode the semantic LiDAR point cloud as conditional input to guide the denoiser. The target scene is obtained by subtracting the estimated residuals from the noisy ground truth. To regularize the estimated noise, we employ both local and global losses. The local term directly compares the estimated noise with the injected noise, while the global term regularizes the statistical characteristics of the estimated noise in the spatial and semantic domains. We evaluated DiffSSC on the Semantic Kitty benchmark. However, since Semantic Kitty only covers the front half of LiDAR scans, we conducted extended experiments in a panoramic scenario. To fairly compare with baselines, we first split the panoramic sweep into two halves and fed them separately into the baselines. After generating the two halves of the scene, we rotated the rear half and concatenated it with the front half to form the panoramic scene. Here are the results of the panoramic experiment on our approach and the baselines. On Semantic Kitty, the baselines show discontinuous predictions at the boundary between the front and rear segments, while our DiffSSC predicts more accurate background semantic categories. On SSC Bench, DiffSSC also provides continuous predictions and accurate semantic segmentation. We conducted ablation studies at both the module and policy levels. Comparing ABC reveals that the performance is mainly driven by the diffusion model, with the refinement stage only slightly enhancing the density. CDE reflects the noise schedule, and CF demonstrates that global regularization significantly improves performance. Thanks for watching.